Hello, welcome back. This is Dr. Oz from Western Kentucky University. Today we're going to go through an exercise where we're going to apply the integration techniques that we learned in the previous chapter. So in particular, we're going to try to solve a differential equation by the technique called separation of variables. In particular, we have the differential equation given in the form of 1 plus x squared y prime minus 2xy equals 0. Our task is to determine the unknown function y. So the question again is asking what is exactly y, so that when you take the derivative of that and multiply it by 1 plus x squared and subtract it from 2x times itself is going to be equal to 0. This kind of differential equation is slightly different from what we had done in the previous chapters, because those that we went through earlier were in the form of finding the antiderivatives directly, but this one is not in that form, and y's and x's are sort of like mixed up. So what we're going to do here is that if we can, we're going to try to separate the variables x and y. In other words, we're going to collect all x terms in one side of the equation and all y terms in the other side of the equation. This technique allows to find the antiderivatives of both sides of the equation, which is in fact integration of both sides of the equation. But before doing that, why don't we sort of like rewrite this equation in a way that we sort of like add 2xy to the both sides of the equation, so that now we have the equality of this sort. So again, as I said, we're going to collect all the y terms in one side, x terms in the other side. So why don't we divide both sides by 1 plus x squared and y. So this way I can cancel 1 plus x squares here and then also y terms here. In turn, we have y prime over y on the left, and then 2x over 1 plus x squared on the right. So as you see that the variables are sort of like separated here, and the separation of variables says that you can integrate both sides simultaneously with respect to x. So what that means is I'm going to put the dx here to show that the integral is on x, and the same thing here, so this would be 2x dx divided by 1 plus x squared. So now we should utilize the U substitution for each integral. Okay, but just keep in mind that if you start with the y function, okay, dy is defined as y prime dx. So differential of y is defined as y prime dx. So what that means is the left-hand side of the integral can be written as dy over y, right? Because the whole top, y prime dx, is just dy, the bottom is still y. So this is the integral of dy over y. And then this one, why don't we call here u to be the bottom, since the derivative of the bottom, which is du, is just 2x dx. So this is a good application of U substitution because 2x dx is right at the top. So I can replace that by du and the bottom by u. So as you see that these two integrals are converted into something really easy to work with. All right, so for these two integrals, we have the log rule to be applied directly. That implies, in fact, the left integral is ln of the absolute value of y, and the right-hand side integral is ln of the absolute value of u, because again, this integral is on y, this integral is on u, so we have to be very careful on that. But u was originally 1 plus x squared, so we can go back to the main variable, and we do not forget to put an integration constant here, because we integrate both sides. In fact, you can put an integrating constant to both sides of the equation, but it's not necessary because the difference of those constants is still arbitrary, so we can just call it just c. So at this moment, you can go ahead and simplify this expression a little bit more by using the properties of ln. So in other words, I can subtract ln of 1 plus x squared from both sides of the equation. and the right-hand side is just arbitrary constant c. And when you have two ln expressions subtracted, you can write it as ln of y over 1 plus x squared. Again, this is a property we have seen in pre-calculus section. I think it's 1.5 or 1.6, so you can go back and check that this property is listed in the corresponding section. And once you have ln type equation, you can always rewrite this equation in a way that the absolute value of y divided by 1 plus x squared is e to the c. Okay, so this is sort of like how you go from here to here. Since 1 plus x squared is positive, so I can multiply both sides of the equation by that. So y becomes e to the c times 1 plus x squared. So this is sort of like the final form of the solution. In other words, the explicit form of the solution to this differential equation. And in certain cases, you can actually replace e to the c by another constant d, because if c is arbitrary, then e to the c is going to be arbitrary. So the solution form would look like d times arbitrary constant times 1 plus x squared. And the final form of the solution is called the general solution to the differential equation. And this is the best form that you can get. In fact, at this moment, you can also stop and conclude that you have the general solution, but this is more like the implicit form. This is more like an implicit form. Still implicit form, and still implicit form, but the final form is in fact explicit because you just state it as y equals a function of x. All right, this is the end of the video. Thanks for watching. I'll see you in another video. Bye.